Okay, continuing through section 12-2, our discussion on vectors, we're on problem 10. So let's give it a look. It says, find the sum of the given vectors. A equals minus 5, 4, and B equals 6, minus 1. So they want us to add A and B. And that is just going to be the x component of A plus the x component of B, comma, the y component of A plus the y component of B. This will equal 1, 3, which we have there. Okay, now how to plot this? Okay, we have x, y, and let's actually show both of these vectors. Okay, so we have, let's try to use color to help us. Blue. Actually, let's do green for A. Negative 5, 4. So A is going to point from the origin to this point. And let's do, how about red for vector B. 6, negative 1. It's going to go from the origin to this point. And then the resultant of adding those two up, what we can do is we can put the tip of B onto the, the tail of B onto the tip of A, and we can, actually let me write the resultant in first. So we know A plus B is 1, 3. So that's A plus B. Now, if I were to translate B, so I can move it up and to the left, as long as I keep its angle the same, it would look like that. So you can see that if we got from the origin, went down A, and then added the B vector to it, we would end up with the resultant A plus B. We would end up at the same spot. And hopefully you can see if I drew this to scale that this B up here is parallel to this B down here, and it's the same length. And if you look at it, the best picture is this one. So that's pretty much what I drew. Okay, that's problem 10. Okay, problem 11, very, very similar. We have another A and B, and then we want to add them together, this time in 3 dimensions. So we take the x component of A plus the y component of B, which is 0. Excuse me, the x component of A plus the x component of B, comma, the y component of A, 0, plus the y component of B, 7, comma, the z component of A, 3, plus the z component of B, 0. And this is a kind of a sparse vector, not much to it. 2, 7, 3. Well, actually, that one's kind of full. But the vectors that compose it had a lot of zeros in them, which is going to be kind of nice because then they won't, the 3-dimensionality of it might kind of collapse a bit and it'd be easier to draw. Okay, so let me draw it the same way they have it, x, y, and z. And let's see, we need 2 in the x at least. And the z, the highest it goes is 3. Okay, so let's try to draw in our vectors. So let's do A in green. 2 in the x, 0 in the y, 3 in the z. So it's going to be, if I draw like a dashed line here, 2 and then 2, so it's going to intersect right there. From the origin, that is A. Okay, then for B, let's do it in red. 0 in the x, 7 in the y, 0 in the z. So it's a very simple vector. It goes right along the y-axis. Doesn't go up, doesn't come towards us. And then the resultant, this one's going to be kind of hard to graph because it's all 3 dimensions. We have 2 in the x, 7 in the y, so we have to project that. So this 2 and that 7, so that's part of it. But then it's going to go 3 in the z, so we project this. Then we also have to project it along the x direction. So it's going to be up like it's hard to draw this. So it's going to look something like that. So that's a plus b. And let's see that difference between that difference and our answer. So just like before, the only difference between this one and our answer is they have drawn b like that. So they have translated b up and to the left, and otherwise you can see my a looks pretty similar to theirs, my resultant looks similar to theirs, and then the only difference is I drew b down here when they brought it up here. Okay, so that's problem 11. Okay, another one very similar. So we have a plus b, 1 plus 0, comma, 3 plus 0, comma, minus 2 plus 8. So we're going to get 1, 3, and 6. And we put that there. And I'm not going to try to plot this because I've shown you several times now, and you can see that it's a lot harder for me to do it by hand than they get with their computer-generated pictures. So if you imagine drawing these, you'll get this one right here. So I encourage you to practice that, but I think I've shown you enough now where you can probably skip me kind of fumbling around by hand to do that. Okay, 13 is a different type of problem, and in this one they give us 2 vectors in component form where we have I and j representing x and y, and the first one is they want us to add this. So adding a plus b, again you just put the i's with the i's, so 2 plus 1 on the I component, and then you do the j's with the j's, so the j for a is 1, the j for b is minus 5, and that's going to equal 3i minus 4j. So that would be the combination of those components. Okay, now they want us to double A and triple B and then add them. So double A, triple B, and add them. So we're going to get double A would be 4, so 2 times 2 is 4, and then tripling 1 would be 3. So I had to triple the 1 in front of the I component of the B vector, and I had to double the 2, which is in front of the I component of the A vector, and I get 4 and 3. Plus, double the J component of A, which is just 1, so now it's 2. Plus, but it's actually going to be minus because it's a minus 5. Triple that minus 5, which would be minus 15 on the J. And we'll end up with 7i minus 13j. Okay, then the third part says find the magnitude of A. So the magnitude of A is its length, and we just use Pythagorean theorem to get it. So we take the I component squared plus the J component squared, and we get the square root of 4 plus 1, which is root 5. So that would be the length of that vector A. Now they want us to find the length of the difference of A and B. So first we have to find the difference of A and B vectors, subtract them, and then calculate the magnitude. So the difference of those two vectors would be 2 minus 1 on the I plus 1 minus minus 5 on the J, which would equal the magnitude of 1i, let's see here, plus 1 minus minus 5 would be 1 plus 5, 6 in the j component. And just Pythagorean theorem those, it would be 1 squared plus 6 squared, square root of 1 plus 36. Root 37 does not simplify, so we call it root 37. Okay, so a little bit different, but still not overly, hopefully not too bad. Okay, that's problem 13. Okay, in problem 14, they want us to find a unit vector. And they gave us a three-dimensional vector, 8i minus 1j plus 4k. Well, to find a unit vector, so let's call this vector v. So a unit vector is equal to v divided by the magnitude of v. So let's find the magnitude of v. That would be the square root of each component squared, so 8 squared. Now it's technically minus 1 for the j component, but when I square it, it's going to become positive 1, and then it's plus 4 squared. So this is going to be 64 plus 16 plus 1, and if you do that, you will get, it's the square root of 81, which is a nice number, which means that's 9. So what we do is we put the original vector 8i minus j plus 4k, and we divide each term by 9. So we're going to get, let me do this down here, 8/9 on the I vector minus 1/9 on the j vector plus 4/9 on the k vector. And you would look to see if any of those things can be simplified, and they can't. So you just type them like fractions like that. Problem 14. Okay, in 15, they give us a three-dimensional vector, minus 6, 4, 4, but they say we want a vector in the same direction of that, but it has length 6. So what we're going to do is we're basically going to find the magnitude of the vector as is, and then divide that into 6, and then multiply the original vector by that, and it should factor the vector down or up depending on what this magnitude is. So let's find the magnitude of this vector. It'd be the square root of minus 6 squared plus 4 squared plus 4 squared. And if you do that, you get 36 plus 16 plus 16, which is 32 plus 36. You're going to get the square root of 68. And the square root of 68 is the same as 4 times 17. And that 4 can come out of the square root as a 2. So you get 2 root 17. So what we're going to do is we're going to say the new vector, we're going to multiply that by 6, the length we want, divided by its current length magnitude, which is 2 root 17. So in essence, we're making, when we divide by 2 root 17, we're making a unit vector, which has length of 1. Then when we pull the 6 in, it will then stretch that length out to 6. So we're just going to take, notice 6 can be divided by 2, so you get 3 over root 17 times this vector. So we have minus 6, 4, and 4. And so what we're going to get is we're going to get minus 18 over root 17. Just minus 6 times 3. 4 times 3 is 12, divided by that root 17. And then this 4 times 3 is also 12, divided by that root 17. So that would be the vector you would type in. Okay, problem 15. Okay, so it says, they give us a vector, it says, it says vector v lies in the first quadrant and makes an angle pi over 3 with the positive x-axis, and the length of the vector v is equal to 6. So pi over 3 is 60 degrees, so it's going to look about like that. And we know the total length of that vector is 6. Let me not write that in because it'll get cluttered. But we also know that this angle right here is pi over 3. So they want us to break this into its components. And it turns out that the x component of a vector, I think I showed this before, is the magnitude of the vector, and I should say this is the magnitude of that. It's just purely the length. It's the magnitude of the whole vector times the cosine of this angle theta. So we call this angle right here theta. And we can actually, let me write right below that, and then the other one, if I have room, the y direction component is equal to the length of the vector times the sine of theta. So we just have to plug in what we know. We know this is 6. We know this is pi over 3. Make sure you're in radians on your calculator. This is 6. This is sine pi over 3. And it turns out that cosine of pi over 3 is root 3 over 2. No, wait. Pi over 3 cosine is 1/2. So this is times 1/2. And sine of pi over 3 is root 3 over 2. So you could use unit circle to get that also. You don't have to just dump it in your calculator. So the x component is 3. And the y component of v is 3 root 3. 6 divided by 2 with a root 3 on it. Okay, and then the last step is just to put this in vector notation like this. And that would do it. Okay, so that's problem 16. Okay, problem 17 is very interesting. It's going to be very useful if you go into like physics or engineering especially. So they give us two vectors, A and B, and A is at 45 degrees from the horizontal, and B is negative 30. In fact, that's kind of important to put that in there. This is negative 30 degrees with the horizontal. And they want us to find a resultant vector. So it'd be like, usually we look at this as forces, so, and actually they're saying forces, so there's some force pulling at 45 degrees up, and then there's another force pulling on this object 30 degrees down, with different magnitudes of those forces. And so we just have to use the same equation we just used. We have to break each force down into its x and y components and then add them up. So AX, the magnitude of the force in the x direction of A, is going to equal 22, which is its magnitude, times the cosine of 45 degrees. And I'm going to do these, let me do these in different colors so we're okay with it. AY, the y direction force, is going to be 22 pounds times the sine of 45 degrees. Okay, and if you do this out, you should get on your calculator the oh, you know what? I wrote the final answer. So you're going to get 11 root 2. So it turns out that cosine of 45 is root 2 over 2. So divide 22 by 2, you get 11, and then there's root 2 on it. And it's actually the exact same value for sine. So you get 11 root 2 for both. Okay, and then we're going to do the b component. So the x direction of the b vector, it has a different magnitude, 14. So it's 14 times cosine, be careful here, negative 30 degrees. And then the y component of b is going to be that 14 times the sine of negative 30 degrees. Cosine of negative 30 is root 3 over 2. So you get, actually I better show that, 14 times root 3 over 2. So it's going to be 7 root 3. Sine of negative 30 is 1/2. So we're going to get 7. Okay, now the reaction force is the combination of these two things. So the reaction force in the x direction is equal to 11 root 2 plus 7 root 3. And I carried these exact numbers, but it actually wants the answers in decimal. So you can convert this to a decimal, and it turns out it will be 27.68. Okay, the reaction force in the y direction is going to be the summation of 11 root 2. Oh, there's a key thing I missed there. Glad I caught it now. Notice that B is pointing into the fourth quadrant. In the fourth quadrant, all x values are positive, but all y values are negative. So this is actually a negative half, which makes this a negative 7, which makes this 11 root 2 minus 7. And if you do that in your calculator in decimal form, you should get 8.55. So if we were to plot this, this vector would have a length of 27 in the x and 8 in the y. So it would, it would truly, if you plotted this, kind of look like this. It's going to be longer in the x than both because both are pushing in the x direction. So the overall length in the x direction will be longer. And then B is pulling A down. It's still positive though, so that's how it would look. One way you can actually do this graphically is you can put both vectors parallel to each other, and then that should give you the result. Make a parallelogram. Okay, but we have to find the overall magnitude. So the overall magnitude of the reaction force with no x or y on it, let me get rid of that. So the reaction force R, the overall magnitude of that is equal to the square root of its components squared. So we would get the magnitude of R is the square root of 27.68 squared plus 8.55 squared. Square rooted. And if you do this correctly, square those two numbers and take a square root, you should get 28.97. Now, they want the final answer to one decimal place. That's why I kept 2 decimals. So, in fact, I might actually keep 3 decimals. So, I don't want to make a rounding mistake. So, if they want 1 decimal, I keep 2 or 3. Okay, now, to round this to 1 decimal place, this is one of those rare cases where the 7 is going to make this a 10, which is going to make that 8 a 9. So this would be 29.0. Okay, which is what we have right there. Okay, now for the angle. Boy, I ran out of room. Let me get rid of some of this so I can do the angle. Okay, the angle comes from trig, and let's just draw this triangle. So we know we have this resultant. It has an x component, it has a y component. This is 90 degrees. This length is 27.68. This length is 8.55. And we don't actually need it, but I'll write it in. This length is 28.97. This is theta. So to find theta, the easiest way is to use the opposite side and the adjacent side because I have a good sense that those are right. Or at least if I make a mistake in calculating the hypotenuse, then that adds another possibility for me to make a mistake. So you could use any of the trig functions, SOHCAHTOA, to solve for this angle, but we generally use tangent. So we can say, hey, the tangent of theta is going to be the reaction force y divided by the reaction force x. So tangent is opposite over adjacent. And on this drawing, the opposite side is the magnitude of ry, and the adjacent side is the magnitude rx. So to solve for theta, we have to take an arctangent. So we arctangent ry divided by rx. And we have those numbers. it's just 8.55 for RY, 27.68 for RX, and if you arctangent that in your calculator in degree mode, because I want degrees here, you should get 17.165 degrees. 16 degrees. Okay. And when we round to one decimal place, we'll call it 17.2. Kind of a, I'll admit, kind of a long problem, but a useful one. You'll see these a lot, especially, like I say, if you do physics or engineering. You'll do a lot of force balance problems where you decompose these forces into their x, y, and even z components. And then you add all the components that match, x's with x's, y's with y's, z's with z's, and you can find the overall resultant. Yeah, that's 17. Okay, 18, we're starting to get into some real tough problems here. It says find the unit vectors that are parallel to the tangent line to the curve y equals 2 sine x at the point pi over 6 comma 1. So, when you see the words to the tangent line of the curve, that is a derivative. So when you see those words, you got to think derivative. So they gave us the curve y equals 2 sine x, but we actually have to find the derivative of that. So you'll have to dig into your calculus 1 knowledge. Y prime of sine is cosine. So the derivative of sine is cosine. Any number in front just hangs on for the ride. And it's at the point x equals pi over 6 and y equals 1. So we're going to plug that x into this derivative. So we're going to plug 2 cosine the x value pi over 6. We're actually not going to use the y value. Pi over 6. And cosine of pi over 6, cosine of 30 degrees, is, I always forget this one, is it a half? It's root 3 over 2. So we're going to get root 3 over 2. And these 2's will cancel, so this whole thing is root 3. Now that is called the slope of the tangent line. So we just found the slope of that tangent line. So the value of the vector that will, and let's just work off of this solution. So basically we have found a line that's going to go through that dot right there. And we know it's x, the slope is root 3 over 1. So this line that's tangent has a slope of root 3 over 1. So it's root 3 in the y, 1 in the x. So let's actually write that, 1. So we can write that as a vector if we write it as, let me see the best way to write this, the unit vector that is parallel to the original vector would equal 1 in the I, that's this part, plus root 3 in the j. That's this part. From the slope of the tangent line. But to make it a unit vector, we have to divide by the square root of these numbers squared. So we take 1 squared plus root 3 squared. And we will get, this is 1i plus root 3j divided by 1 plus 3, because square root of 3 squared is 3, plus 1 will be 4, square root of 4 is 2. So it turns out to be pretty nice. The unit vector that's parallel to the original vector, the unit vector that is parallel to this dot that we have found, point pi over 6, 1, is 1/2 I plus root 3 over 2j. Now that's one answer, it's right here, factoring out the 1/2. There's another answer, and that's the positive, that's the vector pointing this way. There's also a case where the vector can point this way, down. And all you have to do is apply a negative. So just put a negative on the 1/2, and that would be the downward pointing part of the vector. Okay, so now the slope of a perpendicular line is always the reciprocal of the other slope, and it's always the opposite sign. So now for the perpendicular one, we're going to get the vector that's perpendicular is now we swapped. The y value is 1, so we're going to get, and it's minus, so we're going to get minus 1 in the I plus root 3 in the j. No, I did that wrong, sorry. Reverse this. We're going to get minus root 3 in the I plus 1 in the j. There we go. Divided by the square root of these two things squared. Minus root 3 squared plus 1 squared. And it's nice because it's the exact same answer. It's going to be square root of 4, which is 2. So we're going to get minus root 3 over 2 in the I plus 1 over 2 in the j. And that one I have shown right here with the minus sign. And all you have to do is flip everything to get this answer here. Okay, so let's see. And that would give you, wish I used different colors here. So that gives you these two perpendicular vectors. One's positive, one's negative, as shown there. Okay, that's it. So that's problem 18. Okay, last problem in 12.2, 19. They give us three vectors, A, B, and C, 3, 2, 4, minus 1, 9, 1. So I don't think it should be too hard for you to find. This is the drawing for those three vectors. Okay, that I would expect you to take 1 minute on a test to be able to figure that out. Okay, now the hard part is they say there are scalars S and T such that C, the resultant vector, is a linear combination of scalar multiples of A plus some scalar multiple of B. And so the idea here is, how can we stretch A a little bit and stretch B a little bit, or even shrink them, so that when I add them together I get exactly C. So this is actually kind of a common problem to try to face in maybe geometry problem. I want this thing to fit, I have these two lengths, how can I scale them up or down so that they combine correctly? Okay, so here's how we're going to set this up. We're multiplying the A vector by S. So we get 3S plus, we're multiplying the B vector by T. So we're going to get 4T. That has to equal, so what I've done here is the X components of each vector. That has to equal the X component of C, which is 9. And we're going to call that equation 1. Then in the Y component, we're going to take S again times the Y component of A, which is 2, so we're going to get 2S. Plus minus 1 times T. In fact, let me get rid of that plus sign and just call it minus 1. So we're going to take minus 1, the Y component of B, times T, and that has to equal the Y component of C, which is 1. Equation 2. Okay, now there's lots of ways we taught you in college algebra how to solve two equations and two unknowns. You can use substitution, elimination, you can do reduced row echelon form. There's lots of ways. I'm going to show you what I think is probably pretty simple. I'm going to solve for t. So I'm going to add t to both sides of this equation and subtract the 1 and get like that. So all I did was swap 1 and minus 1t, and as they move across the equal sign, they swap signs. Now I'm going to take all of that and plug it into this t right there. So we're going to get 3s plus 4 times the quantity, 2s minus 1. Notice t is gone. It has to equal 9. 3s plus 8s minus 4. Distribute this 4. Has to equal 9. 3s and 8s, 11s, has to equal, add 4 to both sides, 13. Therefore, s has to equal 13 over 11. Then you plug that s into, this is called back substitution, into this s to solve for t. So we would get 2 times s, but we know s is 13 over 11, minus 1 has to equal t. This is 26 over 11 minus, make the same denominator, 11 over 11 equals t. This would be 15 over 11 equals t. And you can find the decimal equivalent of those. It's 1.2 and 1.4, and then the exact answers go right there. So if we, in essence, stretch A by 13 over 11, and we stretch B by 15 over 11, when we add those two vectors, we will exactly reach vector C. That completes section 12-2.